This conference will now be recorded.
Good morning. This is the Yaskawa IQ Wednesday morning training class, and we're going to record a session on the Energy Savings Predictor software that was written specifically for the IQ pump product line from Yaskawa. This allows you to simulate your anticipated application and predict the dollar energy savings that will be realized with the installation of the IQ 1000 versus running the pump across the line. This type of software is normally used to predict the return on investment for the cost of adding the IQ 1000 on the pump system. It is also used to help plan the power system design on a new construction project, and it is also important when you apply for the energy rebate programs for certain utilities that require this sort of analysis. It prints out a very good report. It's a well-integrated piece of software that does the whole job, and it's relatively easy to use. So before we get into that, I emailed a link out to everybody on the Yaskawa class list, and that link will get you to the site where you can download the Energy Savings Predictor. I suggest that you keep the default setting, which is automatic updates, because Yaskawa does update this product not frequently, but enough times that you're going to want to have it updated when you use it. Before I start on the Energy Savings Predictor, I want to cover another subject just because it came up this week, and I try to do this based on the idea that if I am able to help one customer and then replicate that on this class, I can pass that experience on to more people. It's the same principle behind the Yaskawa Solution Center, which you can access on yaskawa.com, and then go to the Training and Support tab and click on Solution Center. This is where the half a dozen or so IQ 1000 applications engineers that man the IQ 1000 helpline publish their significant new work with customers, so that we can benefit from those instances in a published library, if you will, and go and look those things up. Again, relatively well documented, sometimes even with a video. Today we're going to talk about basically networking drives together for sharing the signal from a transducer. It's a relatively simple subject, won't take very long. So I'm going to share the screen here. And this is directly from the Solution Center. And as you can see, we've taken the time to actually put some diagrams in here to show you how to accomplish this task. This basically allows you to take one transducer, which you will see here on the left-hand side. It happens to be a 4 to 20 milliamp transducer. It could be 0 to 10. And it feeds into the main drive. You may not recognize these terminals unless you've done multiplexing, but these are the terminals that allow the drive to communicate via a serial RS-45 network, which happens to speak Modbus protocol, and it's basically a digital communication network between the drives. You can use this up to, I believe, 8 IQ 1000s and 4 in fact, it says right there, and 4 IQ micro drives. This is a communications network. It's how you would set up a multiplexing system where more than one drive operate on the same header. But today we're just talking about sharing a 4 to 20 milliamp transducer between multiple drives. And we will use, in this case, the network. It's a very simple setup. There is a video associated with it, which I'll play for just to set up the multiplexing. It's about 4 minutes.
In this video, I will be explaining how to program a 1000 series IQ pump drive for multiplex operation. The first step is to navigate to the parameter H501 in the programming menu. From the home screen, press the up arrow until the display reads Programming. Press Enter. Change the A to an H using the up arrow and press Enter. Change the 1 to a 5 using the up arrow, then press Enter. With the 01 blinking, press Enter one more time. This allows the value of the parameter H501 to be changed. This parameter, which is the serial communication address of the drive, has to be set differently on each unit. For example, we'll set H501 to equal 01 on this drive. On the next drive, H501 needs to equal a different value, such as 02. The third, H501 to 03, and so on. The next parameter required for multiplex operation is P101. This allows the drive to communicate with other drives on the network. With the 05 blinking, press Escape twice to get the H flashing. Change the H to a P using the up arrow and press Enter. Press Enter 3 more times to change the value of P101. Change this value to a 3 for Memo Bus Network and press Enter. The last parameter is P925, which sets how many drives are communicating on the network. With the 01 flashing, press Escape once to get the 1 flashing. Change the 1 to a 9 and press Enter. Change the 01 to a 25 and press Enter. Now change the value of P925 to equal the number of drives that will be communicating with each other. After all the programming is complete, be sure to cycle power on the drives to ensure the parameters save properly. Make sure the display goes blank before turning power back on. These 3 parameter changes are required for multiplex operation between 1000 series IQ pumps drive.
Okay, so that shows us how to set up the networked version of using one transducer on multiple drives. We have a very simple way of doing it without using the network, and that is shown in the second diagram on the Solution Center document, where we take the 420 milliamp transducer again into the main drive, and we reflect it out to the second drive using the analog output of the first drive. And you set up both A2, the terminal, the analog input on drive 1, and A2 on drive 2 for 4 to 20 milliamp instead of 0 to 10 volt. That's a default setting on the IQ 1000. As you know, you change the parameter associated with terminal A2, and if you were doing this for terminal A1 or A3, the other analog inputs, you would do the same. Basically, you would go to the H parameters associated with analog inputs, those are the H3s, I believe, and change the function of the specific A1, A2, or A3 parameter to 4 to 20 milliamp versus 0 to 10 volt. You then have to go to the control board and change the associated jumper on the control board. It's very simple. It's a little physical square tab jumper that you move from one set of pins to another set of pins, and you would make sure that the pins for the specific analog input, in this case A2, are on the I for current set of pins versus the V for voltage set of pins. So let's assume that we've set up A2 on both drives for 4 to 20 milliamp. We would then also, in the H4 parameters, set up FM on drive 1, which is the analog output, to 4 to 20 milliamp as well. Again, parameter change and jumper change on the control board. Now what we can do is we can flow through the 4 to 20 milliamp, and by the way, this V plus here, that's a misnomer. But this 4 to 20 milliamp transducer will flow into A2. The drive will read it, transfer it to its analog output, which will then transfer to the analog input on drive 2. This is the ability to accomplish this without using the network that we just illustrated a few minutes ago. And I recommend that you do this in 4 to 20 milliamp versus 0 to 10 volt, because the 4 to 20 milliamp signals are more noise immune, especially in the agricultural environment. There is a limitation on the IQ micro in that the output of the IQ micro only is 0 to 10 volt. So therefore I can only transfer the signal to the next drive in 0 to 10 volt, in which case I recommend you use shielded cabling and follow the best practices. We have a video on best practices, and those are going out this week to you in terms of recorded classes, so you'll have that. But you could also use an IQ 1000 here and an IQ micro here. The IQ micro still accepts a 4 to 20 milliamp signal on its input. It just cannot output a 4 to 20 milliamp signal on its analog output. So that's the Solution Center document for linking up two drives to one transducer. Now, I'm going to switch the screen and we're going to go and talk about energy savings, but I want to first go over something called the affinity laws, which happen to apply to centrifugal pumping and fans. A fan is nothing really more than a pump of air. So the same principles apply to it in terms of engineering. And the main aspect of the affinity laws that I want to illustrate to you today so that we can better understand the power of the energy savings that we can harvest using a variable frequency drive on a centrifugal pump is that as speed varies from 0 to full speed, The torque varies as the square of the speed. I'll explain what that means in a second. More importantly, the power varies as the cube of the speed. So, the square of a number is the number times itself. 2 times 2 equals 4. 4 equals 2 squared. The cube of a number is the number times itself and times itself again. 2 times 2 times 2. And that is 8. 2 to the 5th is 2 times 2 times 2 times 2 times 2. And if you multiply that out, 2 squared is 4, 2 cubed is 8, 2 to the 4th power is 16, 2 to the 5th power is 32. So you can see that the laws of affinity basically define a non-linear relationship between speed, torque, and the red line is power. 1 times 1 is 1. 1 times 1 times 1 is 1. So, according to the laws of affinity, when we are at full speed, which we will designate as 100% or 1.0, our torque and our horsepower values will be at their unity level, basically the rating of the motor pump system. So if we're talking a 100 horsepower pump here, we're talking about a 100 horsepower pump at full speed. The torque on that, if it's an 1800 RPM motor, happens to be about 300 foot-pounds. If it's a 3600 RPM motor, it's about 150 foot-pounds. But for this discussion, we're really not concerned about torque. We're talking about energy savings of power. So let's, for the rest of this discussion, eliminate this black line and focus on the red line. When we drop to 80% of speed, which is 0.8, we are at 0.8 times the full speed of the motor. So if let me just throw a calculator up here. So 80% of, let's say, 1800 RPM is 1440 RPM. What will the power be at 1440 RPM on a centrifugal pump? We know that the power drawn when we are running the pump's impeller at 1800 RPM is 100 horsepower. But 100 horsepower times 0.8 and again times 0.8 we are drawing 64 horsepower when we drop to 80% speed. We're not drawing 80 horsepower. Actually, no, you know what? Let me just make sure that I do that right. 0.8 times 0. No, it's 0.8 times 0.8 times 0.8 equals, my mistake. We're drawing 51.2 horsepower. A dramatic drop in power, almost half, with a 20% reduction in speed. So now you see why the energy savings of a VFD on a centrifugal pump are so significant. And indeed, the chart kind of bears this out. So when we go to 80% of speed, let me just move this out of the way. you can see that if we follow this line across, our calculation is indeed correct, and we're right around 50% of the power draw on the red line. This is a nonlinear relationship between power and speed. What's more important is think about when you engineer a system and you choose the power rating of your drive, motor, and pump. You're going to oversize it just a little bit. Certainly there's some unanticipated consequences of the design, etc., so you give yourself some service factor. So right off the bat, even if you're running at full capacity, you may not be running at 100% of the power that you've designed, purchased, and installed. So again, using the 100 horsepower example, because the numbers are easy, if I install a 100 horsepower system, my peak demand is probably going to be somewhere less than that, because I give myself a little bit of overhead, service factor. So right off the bat, even when I'm running at peak demand, I'm going to be running at, maybe 90% of full speed. At 90% of full speed, let's do that quickly, times 0.9 times 0.9 times 0.9 is 0.729 times the convenient 100 horsepower of our application. Even at the full capacity, using the drive, because that's how we get the pump to run at 90% speed, otherwise we're running across the line all the time, and by the way, drawing 100 horsepower all the time. So even at the peak capacity of our system, assuming we put about a 10% service factor on our installed equipment, we're only going to be pulling 72.9 horsepower. The drive allows you to run at 72.9 because it can vary the speed of the motor and therefore the pump impeller. Without the drive, you're going to be wasting 17 horsepower. The pump cannot run at anything other than 1800 RPM across the line. Even if you put a soft start on it, it's still going to run at full speed once the soft start ramps it to speed. The soft start is nothing more than a soft start. It doesn't control speed. So with your no VFD pump application, you're always running at full speed, therefore you have no ability to drop the power. What you can do in order to vary your flows, you can put a bypass valve out there or a throttling valve, various ways to vary the flow on the output, but you can't vary the speed of the pump itself. So, most applications do not run at peak power, at peak requirement all the time. Now here's a note. If you do have an application that's always going to run full gate all the time, don't use a drive. Just run that thing on a contactor. Put a soft start on it to reduce the power inrush. But you don't get any energy savings and you don't get any economic justification for the extra cost of the VFD. In the application where you're going to be running at less than capacity, you're going to get energy savings which generate a return on the investment of the installed VFD. And the lower your average speed of your application, the greater your energy savings and the faster your return on investment. If you're running on average 80% of full speed to meet the demand of your crop irrigation or water transfer requirements, what have you, and your average power bill is roughly 12 cents a kilowatt hour, then you're going to pay back your VFD in less than 2 years. We're going to illustrate that with the energy savings predictor in a moment. But that is a significant fact, because basically after 2 years you have a free VFD and you continue to accrue the energy savings costs. This is why it's so important to understand the energy savings of your anticipated application. This is what the Energy Savings Predictor will allow you to do relatively accurately. And you will then be able to make a fact-based decision on the economics of your application. So, in closing, the laws of affinity. The red curve is what we're after. That's the cubed curve of the speed, and it represents the power draw at a specific speed. For example, when we go down to 50% speed, which is roughly here, according to these curves, we are drawing less than 20% of the power. Let's verify that. 0.5 times 0.5 times 0.5 equals times 100. If you are running a 100 horsepower pump at half speed, you are drawing 12.5 horsepower. Now, very few pump systems are going to run down that low, but it gives you the range of power used on a variable speed 100 horsepower pump. Typically from 12.5 up to roughly 52 horsepower if your speed range is between 50 and 80% of the full speed of the pump. So, this is the screen-up page, the home page of the Yaskawa Energy Savings Predictor program. I have emailed a link to everybody in the class this morning so that you can download this program, and I suggest that you, again, allow it to automatically update. If you prefer not to do that, when you screen up the program, look down here in the lower right-hand corner, and it will tell you whether you need an update or not, and then you can choose to update or not. So we're going to start with a new project, and if you're documenting this for regulatory agency purposes, you can fill out all the information. It allows you to choose between a single and a multiplex application. For today, we're going to talk about the single, so we'll start here. These are the steps of the Energy Savings Predictor program. Again, as I said earlier, you have a data page. So we'll start by completing this data, and thus, when the report is issued, it will have all the associated data that you put in at this point. Again, going to the lower right-hand corner. Again, for this demo, I'm not going to, well, okay, we can do this. Demo for Wednesday AM training class. Okay. Note that there's always a little calculator on the lower left-hand corner for your convenience. Let's say that we are P, G, and E. Here is where it's going to ask you for what you're being charged for your power. Now, we could have made this a lot more complicated, because some of the ways that we are charged power from particularly power utilities is pretty complicated based on time usage formulas, time of the day. You know, I just got a smart meter installed up on the ranch, and it basically charges me a different number of cents per kilowatt hour used based on the time of day. In this case, this program is set up for a basic kilowatt hour charge rate, still predominant in most of the utilities that I'm seeing across the country. We'll update this eventually, but it gets a little bit complicated because some of the billing schemes get labyrinthian in terms of how they charge you. So the base rate is your rate that you're charged per kilowatt hour, and we're going to make this 12 because that's typically what PG&E's is. There's an alternate rate for off-peak, and we'll make this 8 cents. And then there's a demand charge. This is where the power utility effectively penalizes you for the maximum power that you use within a given time period. And that can be quite punitive in some cases. We're doing an application in a country called Guyana in South America. I've got Southern California on my brain. Guyana used to be called British Guyana. It was a British colony. It's now an independent country, and it's north of Brazil on the Caribbean Sea. Their power utility is fragile. They are extremely strict about peak power draw. And if you draw power beyond your average, you get charged for the peak, not the average, for the next month. And it only has to be one time. The theory behind this is that if you draw peak power, even one time, the power utility has to have the infrastructure to deliver that peak power. You may draw 1,000 kilowatts on average, but if you draw 5,000 kilowatts one time throughout the month, and the infrastructure is not there to give you 5,000 kilowatts, then you're going to cause a power outage. So the demand charge is justified by the utility or the utility commission, as is the case in California, because of the fact that even if you don't draw the peak all the time, you are requiring that peak to be installed to deliver that power to you when you ask for it, and thus the demand charge. It is an incentive not to draw peak power. It motivates you to put soft starts on things. In the case of the power grid in Guyana, I cite this application even though it's far away because it's a very good example of the fact that a soft start's not a very good peak power limiter. People think of soft starts as peak power limiters. They're not. A soft start doesn't control anything. It's a voltage ramping device. And it is intended primarily to reduce the output torque and shock to the driven system from the electric motor. When you start an electric motor with a contactor called across the line, that motor will pull up to 600% inrush current, but it'll also put a huge torque spike out into the driven equipment. Basically, think about sitting at the traffic light and flooring your accelerator. Well, for those of you that remember what manual transmissions and clutches are, your clutch is in, you floor your accelerator, and you do what we used to call pop the clutch. You just let the clutch out quickly. Well, that car is going to yank itself forward. Your head's going to go back into the headrest, and all kinds of stuff's going to happen in the drivetrain, including probably squealing tires. Not the way you want to start your pump. You may get some jollies from it, the way you do peeling out from a traffic light. But the bottom line is that's not good practice, and it beats up equipment, and it costs money. So a soft start's intended for that sort of thing. The soft start would not limit the inrush current significantly on this application in Guyana, and we had to go to a drive. Even though once up to speed, they didn't vary the speed. So they invested heavily in a drive, specifically to avoid the peak power demand charge, and the drive effectively ramped the pump motor to speed without exceeding full load amperage, in other words, running amps. A drive can do that. A soft start cannot do that. So at this point, this application was justified primarily because we didn't exceed running amps during the ramp up to full speed on this particular set of pumps. So let's leave the demand charge where it is. You're typically charged in kilowatts versus kVA. The power company has to deliver kVA. What you use in terms of the work you do is kilowatts. The efficiency of how you use the power that the power company gives you is kilowatts divided by kVA, or power factor. If you are being charged in kilowatts, you are not being charged for the efficiency with which you use the power. You are not being charged for the power factor. There may be power factor usage penalties on your bill if your power factor is really poor, below 0.8. But typically, if your kilowatt divided by kVA is 0.9 or above, which means your usage is 90% efficient, and that means that when the power company gives you a kVA of power, and kVA equals kilowatts in terms of physics, volts times amps equals watts. So this is a nomenclature issue. But for every, let's say, 1,000 kVA that the power company gives you, if you effectively use 900 kilowatts or more in the actual movement of the water, as opposed to wasting it with harmonic distortion or too many transformer loads or whatnot, then your power factor will be 0.9 or above, and the power company would be pretty happy. Note that very few installations I've been at have had a power factor of 0.9 and above on a VFD, unless the VFD has harmonic distortion, either filtration or active front end, such as the Yaskawa matrix drive. As a point of reference, the Yaskawa matrix drive has a power factor, in other words, its energy usage efficiency, of 0.97 or better, so better than 97%. And that's because its input harmonics are so low. But that's a subject for a different class. So we're going to have kilowatts. Now, the key to this program is to accurately predict your speeds, your average speeds of usage over, say, a 24-hour period. And as I said earlier, if you're going to run at full speed 100% of the time, so full flow, let's say that we do that, right? This would be a full speed 100% of the time usage curve. This is the more tedious part of the program, but it is also the most important part of the program. So what you see, it won't get rid of that 30%, will it? There it is. Now, this is a 100% full speed all the time curve. Here, you will get no energy savings using a drive. Actually, what you will get is the efficiency. You'll get the cost of the drive and the drive's inefficiency, which typically is going to be about 3 or 4 or 5%. So the drive will actually cost you money with no return on investment. However, this is a normal usage curve, where you can see that the peak or most often used speed is roughly around 70%. This curve actually goes out to 100%. This person did not size any service factor over his peak requirement. Most curves will not have a 100% factor. This whole chart here will be shifted a little bit to the left based on your service factor. So what is very important is that you fill out this column as reasonably accurately as you can. This is the crux of the accuracy of the energy savings predictor. You can typically go with our default curve because this is the default curve for a centrifugal pump on an irrigation system. This is our experience. This is our average experience over thousands of pumps that we've installed, or thousands of IQ 1000 drives we've installed on pumps. Okay, so let's go to the rest of the data. We're talking about a pump. This is the only thing we can do with this particular program because it's dedicated to pump. If we are comparing this system here is, what if we weren't using a drive? This particular item here, to control the flow, we would either use a bypass valve or we would use a discharge valve. And then you want to enter your minimum head in feet. Here's your motor data. This is pretty straightforward. Let's, oops. Okay. Typically we're going to be at 460 volts, 124 amps, it self-corrects. This efficiency is based on the federal EPAC standard efficiencies for NEMA rated motors. Your submersible motor may not have that rating, in which case you would go here and you would enter whatever value the submersible pump manufacturer tells you is the proper efficiency. If you're within a percent or so, it really isn't going to make a big difference in the ultimate results. Here's where you put in your drive installation data, and as you see, we selected 100 horsepower, and the drive selection is already done for you. Okay, in this particular case, we can't use a micro. You might be able to use an IQ U1000 matrix drive, but it's already selected the drive for you. There's the data on the drive. Really? I didn't realize that our 100 horsepower drive only weighed 99 pounds. What are we doing? Well, that's obviously just the drive itself. When it comes in the configured cabinet, which you typically buy, you have the NEMA 3R white box. It's going to be way a bit more than that. So, whatever your drive cost is, now, installed cost, that's what you want to put in here to get a true return on investment, because that's the real dollars that you're spending. So let's say you buy the drive and then you put it in a can, or you buy the drive in a can from Yaskawa in the configured package through Preferred Pump, and that's what Preferred Pump stocks, by the way, is our NEMA 3R configured. And by the time you get all done with that and you basically pour the pad, you drop the box onto the pad, and then you power it up from the power pole transformer, you're going to be into probably close to 3 times this cost. So we're going to put in $33,000. Actually, let's do this. Follow it. $18,000 for the drive in a box, and then install costs. Let's say we'll put that at $12,000. Is there any rebate? Well, the PG&E rebate is, I believe, $50 a horsepower for non-compliant. And then if you comply to other aspects of their specification, you get more than that. But as I understand it, the way that the PG&E spec is written is to comply to the higher levels and get the higher level rebates costs more than the money that you get back. So the base rebate is typically what people are going to be applying for. So let's say it's $50 a horsepower times 100 horsepower, that's $5,000. Okay? Now, hours per day of operation, 24/7, maybe. Let's just be conservative and put in 8. And, oh, wait a minute, did I? Yeah, this is not what I want to put here. I want to put the $5,000 here, because that's the utility rebate, one time. And it's dollars per system, and we have one system. Okay, so now we have this page filled out. Now we're going to go to the energy savings estimation. This is where the program does its thing. So your energy usage with the system that's using the bypass valve or the discharge valve will draw 189,000 kilowatt hours. Using a drive with the average usage bar chart that we did on the previous page, we would draw 94,825 kilowatt hours. The energy saved is this. Here's our costs to install, and we even calculate a carbon footprint because there are some areas where you get carbon credits. I'm not quite sure how that works from state to state because the legislation is different in every place that I've asked about it. But this carbon footprint tonnage is used for those legislative situations. So the yearly savings is $11,184. And your system payback, return on investment, is 2.235 years. What that means is that for the amount of money you spend to install this system, you will receive that money back in energy savings in 2.235 years. After that, you still receive the savings, but you've paid off the equipment. And at that point, the money goes into your pocket. So we have a variety of other pieces of data that this program provides for you. There is your cash flow analysis. In the first year, you're going to spend this much money, $30,000 minus the rebate from PG&E, minus the demand savings and the energy saved. Here's your total outlay in cash in the first year. Here's your total outlay in cash in the second year. In the third year, you have a net positive cash flow. You're making money. And onward. In review, there's the duty cycle. Here's your dollar payback over time. You're negative up to 2.2 odd years. Beyond that, you're positive cash flow. Power requirement in kilowatts based on the percentage of flow. The red is your discharge valve, which we selected as the base system. The blue is the energy drawn from the drive. Note, at 100% demand, the drive pulls more than the motor across the line. Here the discharge valve will be open completely. This is the efficiency of the drive, the difference between the red and the blue. There's your energy usage over your duty cycle that you entered in. So you can see there's a variety of pieces of data that the regulatory agency is going to want to see. And the program is a convenient way of reporting that. Now, let's go to the final report. And Yaskawa has done a pretty good job here in giving you options to print, export to PDF, export to various other formats. Typically PDF is what's used. And then you can print it, email it, as you will. These reports have been relatively well received by the utility evaluators for their energy savings rebate programs. We're not the only company that has one, by the way. Typically every drive manufacturer that's involved in the agricultural pumping market is going to have an energy savings predictor program very similar to this one. I've looked at several of the other ones and they're all pretty much the same in terms of function. Some of them look suspiciously like they've been written by the same person and just different banners put on there. That's fine. I'm all for consistency in reporting. So, there's your energy savings report. This is what will be published, depending on whether you decide to email it, export it to a PDF, etc. And that's everything that I showed you earlier, encapsulated in one PDF file. So, this is the conclusion of the class, the Yaskawa Wednesday morning IQ training class for the Energy Savings Predictor. Again, you can download this from yaskawa.com. You can go to yaskawa.com, type in Energy Savings Predictor, and it will get you to the page where you can select between the Industrial Energy Savings Predictor and the IQ 1000 Energy Savings Predictor. I have emailed you the link to the IQ 1000 Energy Savings Predictor. I hope this has been helpful to you, and we will publish this recorded class. But for now, that's all I have to say. We're 6 minutes early. I'll end this class with, again, a thank you for those of you that have attended, and hopefully this information is useful for you. So I wish you a good day. It's 7:54, time to go to work. See you next week.